Oh, muted. So, hi guys. Uh, how was the contest? How did you guys find it? Let's wait a bit, I guess, for more people to come here before we start the discussion. Yeah. Hi. Hi, Dylan. Guys, kung nasa chat kayo, huwag kayong matakot na magpakita. This is just like a community thing anyway, where we just hang out and solve problems, I guess. Kaya, okay lang. Let's see. Math forces. Yeah, if you compare the contest to last week, this week's problems are very uh mathy, think heavy. Oh shoot. Yeah. Pero cause there are sort of many different. Oh my god, my. Cause there are like many different uh sort of styles of problems, I'd say, and the problems we had this week, they're one of them. If you compare it to last week's, like let's say last week's C, which was basically just code, or last week's D, which was basically think for a while and then code for a while. This week's problem set is like think think for a while and then think more and then you code a bit. So um yeah, getting used to these different flavors is something you're going to have to learn. But that's okay. We're going to go through all of them here. Okay, let's see. Sino pa ba nandyan? Here. Okay. Sige. We'll start at 4:06-ish. I'm just uh waiting for more people to come. Yeah. Slide that. Okay. Yun. Uh, okay lang ba yung okay lang ba yung stream? Malinaw ba yung code? Okay lang ba yung volume ng boses ko nung BGM? Okay. Okay. Sige. So let's start going over the problems now. So magpapakilala lang muna ako dito because this is my first time showing up here. So hi, I'm Dan. I'm basically an alumni of NOIPH. I am now studying in Singapore. I think information security. Not sure. Yeah, I'm not. I'm personally not sure why I chose that. But oh well. Anyway, yun. You can see me in the server sometimes, but not always, cause I don't tend to interfere with whatever the new kids are doing, cause new kids are cool. Cisco. Hi, Cisco. Thanks for the BGM suggestion. Yeah, it was him who um suggested that I use this music if any one of you guys in the chat recognizes it. So okay. Also, just to give credit where credit is due, this week's problems are from CJ Kines, also a former, no, not former, also an NY alumni. If you guys do, if you guys did competitive math back then, his name might be familiar. His name still might be familiar. He's great. He's a great author, I guess, a great teacher of math stuff, and also a great programmer. So yeah, he was the one who came up with these problems. So let's get right into the discussion. Okay, so here we have problem a beautiful, cute, delightful sequence. Haha, ABKD. Okay, uh, so Abby likes sequences. She makes a sequence A. The terms of the sequences are written as, okay, personally for me, if I were um taking, if let's say me from like 10 years ago or like 5, even probably 5 years ago, were to read this contest, the first thing they'd probably think of would be, oh no, sequences, hey, what the heck is going on? And then they'd probably spend let's say 10 or so 20 minutes just trying to figure out what the hell is going on. Bakit biglang may A na lumitaw? Bakit walang limit sa number ng A? Same, yeah. I relate. And like, in the best case, eventually I'd figure out what was going on and just get on with figuring out the solution. In the worst case, I'd just completely die. And sometimes, just completely dying still happens to me, even now. If I don't get what's going on, or I think it's too complex for me, or I can't find a first insight in. But I make sure that even in those cases, I try. So here, we're confronted with sort of this unfamiliar definition. And so the first thing, the very first thing, before we write a single line of code, before we try to figure out a single thing about this problem, the first thing we have to do is to not panic. Okay, I know it's way easier said than done, but just take a deep breath and just accept, okay, we have this sequence, and so how are we going to deal with it? So the terms of the sequence are written as way easier said. Yes. We're going to go over everything slowly. So okay, the terms of the sequence are written as a sub 1, a sub 2, a sub 3, and so on. So we have this sequence A. Um, I guess you can sort of imagine that it almost looks like um it almost looks like as if I had an array A, and uh the terms of the array are A1, A2, A3, and so on, right? So this sort of notation to communicate that you have this sequence with these values, it's common in math. Particularly, I think it was used among all the problems here in this contest. So yeah, I do suggest you try to get familiar with it. That's the other benefit of not panicking, which is that you allow yourself to be exposed to these kinds of patterns, to this notation, and as you go on, eventually you'll find that this notation sort of makes things clear, because instead of saying, oh, Wait, how do I say this? Instead of saying the first term of the sequence, the second term of the sequence, you can just read, oh, A1, and oh, you'll instantly recognize that this is the first term of the sequence. And as you go further, you'll find you yourself using this notation, even if nothing explicitly told you to, just because it makes things clear for yourself. Of course, you can end up doing things a different way. That's sort of one of the good things about programming, which is that as long as the computer understands you, and if you're, say, working in a group context, as long as other people, your teammates, understand you, then it's okay. Do whatever the hell you want. So that's what we have for a sequence. She uses these rules to make the sequence. So we're given a set of rules to make a sequence, and let's see how the rules go. So the first term, ace of one. Me, the way I was taught things, I say a sub one because if you think about it, the one is like underneath the A, so it's sub of the A. So yeah, a sub one. It's definitely possible though to say things like uh A1 or whatever. Again, as long as you're understood. So wait, let me just check. Did the Facebook stream die? Wait. That's weird. Huh. Okay. Anyway. So the first term is 1. So we have let's just switch real quick. Okay. So we have a sequence. So we have that the first term of the sequence, which we can write as, oh my god, my computer cannot handle this stream. Wait. Oh, wait. One sec. Yeah. Okay. Wait, everything's loading. Okay, so the first term of the sequence, a sub 1. Okay. Is 1. Okay. And then we're given that the second term, a sub 2, is the smallest positive integer such that a1 plus a2 is a prime number. What the hell does that mean? Okay, so there are several things that we have to break down. So a sub 2 is the smallest wait, my handwriting is a bit bad today for some reason. Is the smallest positive integer, okay, such that a sub 1 plus a sub 2 is prime. Okay, just a vibe check sa chat. Do you guys know what a prime number is or not? Okay, I'm just going to go ahead and explain it anyway, in case. So, since you probably learned it already. So, basically, a prime number is a number such that, because you can factor numbers into smaller numbers, right? So, for example, let's say you have number 6, right? You can write 6 as 2 times 3, or let's say number 10, you can write this as, let's say, 2 times 5. 2, 3, 5, 7, 11. Yes, those are examples of prime numbers. I'll get into that later. So, for other numbers, like FB Cuber comments in the chat, we have, let's say, 11. So, with 11, how can we factor 11? We have 1 times 11, but how else? how else are you going to write 11 as the factor of, as the product of two positive integers? Well, you can try to go ahead and if you're kung talagang matigas yung ulo mo, I guess, you can really try hard to go and look for numbers after the stream. But basically, the point is, for some numbers, it's going to be straight up impossible to find another way to factor on the number other than 1 times the number or the number times 1. And these are the numbers we call the prime numbers. Okay. So, okay, just a vibe check lang ulit sa chat. Is 24 prime? Okay, no. That's right. Because you can write 24 as... Actually, there are a lot of ways. You can write it as 4 times 6. You can write it as, let's say, I don't know, 2 times 12. This is supposed to be 2. You can write it as, let's say, 3 times 8, even. So it really just... this is supposed to be 3, this is supposed to be 8. So it really depends. No, that's correct. Good job. Okay. So now... That's what the prime number is. So just to clarify that. Also, one interesting edge case I have to bring up is that how this is. Wait, let me just fix my. I think I erased too much. Wait. Oh my god. A1, A2. Okay. One interesting edge case I have to bring up is that 1 is not prime. Even if you can't write it as the sum of as the product of positive integers other than 1 times 1, it's not prime. There's probably if you go deeper, even deeper into math, there's probably a logical explanation for why it's more convenient when working with primes to say that 1 is not a prime than if 1 is a prime. I don't know it off the top of my head, so I'm not confident saying it here, but we can talk about it in the server afterwards if you want. So that's a prime number. So now we want, okay, so we know what this thing does, right? That's progress. So now we want the smallest positive integer such that this is prime. So how will that look like? Well, we have, so what are possible, let's say the smallest condition is not there, so let's just pretend we're just looking for any random positive integer such that a sub 1 plus a sub 2 is prime. Okay, so a sub 2 is what are possible values of a sub 2. So we try out 1 plus 1, which is 2, and how can you factor 2? Well, you can write it as 1 plus 2. You can write it also as 2 plus 1. 2 times 1, I'm sorry. Times 1. But aside from that, is there really anything else? Well, probably not. So you can probably safely conclude that 2 here is prime. Okay. So, I guess we'll talk later, I guess, in the stream about how safe it is to say safely conclude just from a bunch of examples. But from here, you can look it up you can look it up online, at least the ABaKoDa Round I do, I think. I'm not sure. Or you can write a program to check for yourself that indeed 1 times 2 and 2 times 1 are the only ways to factor 2. And so we can say that 2 is prime. Okay, so wait, I forgot how to erase. I think it's this. Oh my god, I might erase something. Okay. So what are other numbers? So a sub 2 might be 1 plus 2, which is 3. Which, what are the ways to factor 3? 1 times 3, 3 times 1. So again, that's prime. On the other hand, let's test 3. So here we're just trying to get a feel for the definition. This is another thing that I think you can do if you're just completely confused and lost about what to do, which is that you can just try throwing a few examples at it and seeing if the example ends up working. So here, we're just trying to make sense of, okay, since the problem is all about finding since the problem is all about finding this a sub n, then how does the sequence interact with itself? How does a sub 1 talk, so to speak, with a sub 2, a sub 3, a sub 4, and so on? How does a sub 2 talk to a sub 3, a sub 4, and so on? Right. So a sub 2 here can be 3. Okay, just to check. If a sub 2 can be any positive integer such that a sub 1 plus a sub 2 is prime, can a sub 2 be 3? Okay, well, we have that 1 plus 3 is 4, right? And the thing about 4 is, we can write it as the product of two numbers in a non-obvious way, which is 2 times 2. So, it cannot be prime. So 4 is not prime, and so a sub 2 cannot be 3. Okay? So, we can go on here, looking for, let's say, we can test 1 plus 4, 5, it's prime. We can test 1 plus 5, it's 6, so it's not prime, and so on and so forth. But eventually, from these examples, you're going to have to try to deduce something from this. Okay? So, from the integers that we've gathered here, so from the integers that we have here, the ones that can be a sub 2 are 1, 2, not 3, because 4 is okay, 4 is not prime. 4 and 5. That's supposed to be underline my tablet acting weird. So now we have a sense for what this is. Let's bring back the constraint we removed a while ago, which is that a sub 2 has to be the smallest positive integer. Oh my god, what's happening? Okay. So now, among the integers we have here that can possibly be a sub 2, what is the smallest? Right? So the smallest here turns out to be 1. Like, we just spent like 5 minutes running around chasing our own tails just to find that a sub 2 is 1. That's the fun part about math sometimes. You stare at something for a long time and then you figure out the answer and then you facepalm and you realize, oh no, this is so stupid. Why didn't I think of this? Well, this is how you think of it. Just using experimentation, figuring out what's going on. This is a very, if you're sort of experienced, then you'll find that this is sort of a trivial, or this is sort of a simple example, but we're going to add more layers, add more false turns, add more challenges as the contest goes on. Okay, so now that we have the value of a sub 2, let's try to keep going. So let's try to look for a sub 3. So if you read the problem statement, you can see that the third term a sub 3 is the smallest integer such that a sub 1 plus a sub 3 and a sub 2 plus a sub 3 are both prime numbers. So what this means is that now, instead of just worrying about whether a sub 1 plus a sub 2 is a prime number, we now have to worry about two things. First is whether a sub 1 plus a sub 3 is a prime number, and second is whether a sub 2 plus a sub 3 is a prime number. At this point, you might say, oh no, I have two things to worry about now. I can only do one thing right now. How am I supposed to solve this? Okay, breathe. Again, the very first thing you have to do when solving a problem, or trying to solve a problem, or doing any sort of problem solving related activity, is to not panic. We got this, okay? Okay, so let's try to think about this. We know the value of a sub 1. So this funny little a sub 1 plus a sub 3 here is actually, wait, let me just, this is actually a sub 3 plus 1. And we know that the value of a sub 2 is 1. So we have that this funny little a sub 2 plus a sub 3 here is actually just a sub 3 plus 1 also. So they're both a sub 3 plus 1. Right? And the thing is, so we have that this is just the smallest number such that a sub 3 plus 1 is prime. And this is, okay, this is a trick that you will probably often use when you're, let's say, doing competitive programming or problem solving or math or whatever, is that you have to remember the problems you've solved before. So that when you see them again, maybe in a different context or wearing different clothing, so to speak, marirecognize mo sila at magagamit mo sila para ma-solve yung main problem mo ngayon. Okay? So here, we have that this a sub 3 plus 1. Earlier, we spent 5 minutes chasing our own tails willy-wally nagging trying to look for the value of the smallest a sub 2 such that a sub 2 plus 1, I'm writing it as 1 plus a sub 2 just so it formatically fits, but it's a sub 2 plus 1 also. Such that 1 plus a sub 2 is prime, and by looking at the first few values, we find that that value is 1. So, using that past problem to solve our current problem now, what is the value of a sub 3? Okay. Using these ideas that we have so far, a sub 3 plus 1, so the smallest value of a sub 3 is such that a plus 3 plus 1, and the smallest value of a sub 2 such that a sub 2 plus 1 is prime, is really just the same thing. It's just that instead of using the second term of the sequence a sub 2, we now use the third term of the sequence. So the effect of this is that a sub 3 is also really just 1. And probably, seriously, yeah. If the question marks at the end indicate you're being shocked, then sadly, yeah. I'm being serious. It's 1. And now you can start to think, okay, well, what do we have to do in the problem? Cody's favorite number is n. Now he wonders, what is a sub n? Well, clearly we have to keep going, so we have to look for a sub 4, a sub 5, whatever. And judging by this pattern here that we have of 1, 1, 1, the natural question to ask is the next term 1? Well, let's check if it satisfies our definition. So, for 1 to be a good value of a sub 4, it must satisfy that a sub 1 plus a sub 4 is prime. And is a sub 1 plus a sub 4 prime? Yes, it's 2, which is prime. Is a sub 2 plus a sub 4 prime? Yes, it's also 2, which is still prime. Prime numbers don't become non-prime numbers the next day. And is a sub 3 plus a sub 4 prime? it's still 2, so it's still prime. So we know therefore that a sub 4 is 1, and so that probably you can keep this sequence going on forever, because anything plus any of the terms is just any of the terms plus 1, which is 2, which is prime. So from this, we can say that A5, 6, 7, E5, 6, 7, 8, and so on is 1. And that is the solution to problem A. 1. Yeah. Um, there's a little way you might see other people write this, and that's something like wait. Okay. There's a little way you might see other people write this, and that's to say that A sub I equals 1 for all. Oh my gosh, it's not registering right. A sub I equals 1 for all positive I, right? And basically what this means is for any I that satisfies the condition, which is positive integer, then it satisfies this. It satisfies this thing, A sub I equals 1. So I just wanted to note that in case you try to read discussions of similar problems in other places. So now that we know that this is the solution, let's get to coding it. So when coding the solution, you have to be very careful. There are a lot of pitfalls you can encounter and implementation traps and tricky edge cases, and I'm just kidding. I'm just kidding, it's print 1. That's it. We did all the hard work of thinking a while ago. Like I said earlier, this is mostly a contest where you think a lot and then code maybe a little. Unless you want to overcomplicate somehow by computing the value of 1 with some convoluted scheme based on the input. Like, if you wanted to be funny, you could do something like n equals int input. You could take n as input and then like you can print n divided by n or something, and you can run it. My computer is being a bit slow right now, so it might not run. Initialize connected. So input, let's say 5, and we get 1. So that is problem A. If you feel like, if you think that, say, it would be very funny if the problem just asks you to print 1, well, that would actually be sort of, it's not really the same problem. It would be somewhat an easier problem because we wouldn't have to go through all those observations and tactics that we just did a while ago. So okay, with that being said, let's now move on to... Oh wait, I realized you guys can't see my code. Oops. Yeah, it's basically this. That's it. It's print 1. Okay. Do you guys have any questions about how we how about the solution of problem A, or even just the process of trying to find insights and patterns in general? Because this is something we're going to be doing a lot in the next few problems. Okay. Okay, so if there are none, I'm going to be moving on to the next problem. So, let me just pull it up because I don't, yeah, my computer is a bit slow right now because it's handling a lot of things at once. Okay, so problem B. Beautiful, cute, delightful sequence. Uh, okay. So, beautiful Abby-like sequences. She makes a sequence A. Okay, so again, experience from previous problems. We know what sequence means. She makes sequence A. The terms of the sequence are written as A sub 1, A sub 2, A sub 3, and so on. Past experience. We know what this sequence means. It means a string of numbers. She uses these rules to make the sequence. So the first term, A sub 1 is 1. So again, the second term, A sub 2, is the smallest positive integer, such that A sub 1 plus A sub 2 is a composite number. Oh, that's new. A composite number. So sometimes when you have a new definition, sometimes the problem statement gives the definition for you to clarify. So here we can read a composite number is a positive integer greater than 1 that is the product of two smaller positive integers. So a while ago we mentioned that some integers are weird in that you cannot factor them other than in an obvious way. So here we have composite numbers which you can factor in an obvious way. So for example, 6 is a composite number because 6 equals 2 times 3. The first composite number, so here it gives examples. So this is one thing you might want to do if you're stuck on a problem or can't figure out what to do next, is just to read the statement, because I don't know, sometimes you missed a piece of information that turns out to be crucial. For example, I've often experienced trying to think of an overcomplicated, hard, big brain solution when in reality, like, n is just 5 or something, and you can just look for all the possible cases, look for all the systematically search all the possible scenarios. We'll probably get a problem like that later in the future. I'm not so sure. I don't know the problems for the next few weeks. Anyway, or you might just learn something new if you read it differently. So here, um, the first composite numbers are 4, 6, 8, 9, and 10. 5 is not a composite number, because there's no way to factor 5 the uh into two smaller positive integers, right? So what? Okay. So just a vibe check to see if you guys understand the definition. Is one a composite number? Okay. One is not a composite number because you can't factor it as two smaller positive integers. The only thing you can do is 1 times 1. So, if you think about it, 1 is the only positive integer that is not a composite number or a prime number. Like, you can imagine, in a family gathering, you have the composite number branch that's like having their own party, salo-salo, karaoke thing. And then meanwhile, on the other end, you have the prime numbers, um, we're doing this sort of like pamaskot Christmas tree giving out gifts thing, and then you have one who wasn't invited at all. So we'll just F press F to pay respects for one. Okay, moving on. So the third term, a sub 3, is the smallest positive integer. So it's the same thing. So again, past experience, we know how to deal with this, which is to try to look for a pattern. And the fourth term, and this continues in general, blah blah blah. And it's the same thing as problem A. We have to look for the value of any term in the sequence. Let's say we're given 3, we have to look for the third term in the sequence. Okay, so just like before, let's try to find the solution through careful observation. So, let's get back to this screen, and then I go here. Okay, so here we have the same thing almost. So we have that a sub 1 is 1, and then we have that a sub 2. So again, it's the smallest positive integer such that a plus 1 is composite. So right now we don't know anything about what a sub 2 can be. So let's try to find the pattern for it. So we have can a sub 2 be 1, can be 1? Well, that would make it 2. And as we've established from exploring the properties of the sequence in problem A. Wait, oh my gosh. The sequence of here. The properties of sequence A earlier in problem A, 2 is prime, so it cannot be a sub 2. So it has to be 2. It cannot be 1. Maybe 1 plus 2 would work? 1 plus 2 is 3, which is also prime, so it does not work. And then we have 1 plus 3, which would be something like, which gives us 4. And 4, if you recall the list that was shown in the problem, so the first composite numbers are 4, 6, 8, 9, and 10. 4 is a composite number. And since 3 is the smallest that's been shown to work so far, we can have that, we have that, a sub 2 is 3. Let's keep going. Maybe we can find another simple to read pattern from here, like we did the 1 1 1 1 with problem A. Okay. So how do I say this? We have so now we have 2 numbers to worry about. And unlike in problem A, where we can say, oh, a sub 1 and a sub 2 are equal. So in reality we just want the same expression to be prime. Well, in this case, we want it to be composite, right? So now we have 2 numbers to worry about, but that's okay. We can just check both of them at the same time. So we have 1 plus something and 3 plus something. So these numbers both have to be composite, okay? So first of all, we could test out 1 and 2, but even without doing any sort of manipulation, math, or whatever, we can already reject 1 and 2 from being possible candidate values for a sub 3. Does anyone know why this is the case? Okay, so this would be because we've already done the work for them. If you can look here, we already rejected 1 plus 1 and 1 plus 2. We already did the thing, yes, precisely, we already did the thing when we calculated a sub 2. So 1 plus 1 and 1 plus 2, we've already determined them to not be composite numbers. So there's no, well, if you want to be sure, you can do it again. But from a theoretical discovery perspective, wala nang point na ang pag-compute ng 1 plus 1 at 1 plus 2 para i-check 1 o 2 ba ang a sub 3 is just checking past work. There's no need to redo it if you're sure that past work is correct. So this will actually be a theme that you'll uncover later if you try to learn more things in competitive programming. The concept of reusing past work, which is that I already computed this value before, so I don't have to compute this value again now. And often, that simple insight of just being able to reuse past values is already quite a powerful optimization. If you're curious and you want to look things up, the fancy schmancy Google term for what I'm talking about is dynamic programming. But that's kind of an advanced topic. Speaking with where we are right now, so don't worry if everything about that flies over your head for now. We're going to get there soon enough. Okay. Anyway, back to the main topic at hand, which is finding a sub 3. So here we have to test 3 now. So we can test. So we have 1 plus 3 and 3 plus 3. 1 plus 3 is 4 and 3 plus 3 is 6. Right? So if we recall the list of composite numbers we have earlier, we have like 4, 6, 8, 9, 10, and so on and so forth. And we can see that 4 and 6 are indeed both composite numbers. So we know, therefore, that a sub 3 is 3. Right? So wait, let me just undo. Actually, it's not undoing. Anyway, that's supposed to be 3, but it's a B for some reason. Okay, moving on. Let's keep going. So from here, one possible guess that we can have is that the sequence will probably end up just being, let's say, 1... wait. The sequence will probably end up being just 1, 3, 3, 3, 3, and so on. And it's going to be 3 forever. So, how can we verify that this is true? Well, now we're going to look at it from a more wider perspective. We're going to ask about, let's say, so we've already verified the first few terms. So let's ask some random 3 later in the sequence and say, okay, random 3, are you really a 3? So here we can use the definition of the sequence A to check if this value really is a 3, like we've been doing for a sub 2 and a sub 3. But this time, we're not using it to compute a value, we're using it to check if our guess is correct. It's kind of a subtle difference, but if your thought process sort of gets confused, then it might be helpful. So, what are the past terms? Well, the past terms are 1, and the whole lot of bunch of 3s. But again, just as with problem A, where we had a whole bunch of 1s, here it only suffices to check it once. So, again, we're using past work. So here. So we just have to check if 1 plus 3 and 3 plus 3 are composite. But we've already done that here when computing a sub 3. So, from this, it's probably safe to conclude that a sub I is 3 when I is greater... a sub I is 3. Just stopping there is kind of dangerous because you don't account for the fact that the sequence is not 3, 3, 3, 3, 3, it's 1, 3, 3, 3, 3. So you have to put a bit of a restriction by saying that a sub I is 3 if I is greater than 1. Oh my god, why is it? If I is greater than 1. Okay. So, like I said before, think a lot, code a little. So now we're going to do the code a little step. Just to sort of close things out. So if I can just get my code to load, okay. So here we're just going to implement it. Nothing fancy. We've definitely tackled harder things. So we can go compute. We can go read in the input first. And then, since we know the sequence goes 1, 3, 3, 1, 3, 3, 3, and so on, we can just check. Are we dealing with the 1 part or are we dealing with the 3 part? So, now, so to differentiate between the two, we can just use a simple if statement. So we can observe that we'll only have to deal with things that are not 3 if n is equal to 1, right? So just separating cases, logical implementation, things we've covered before. So if n is equal to 1, then we print the value of 1. Otherwise, we print the value of 3. And that's it. You can verify that this works. Let's just run it, just to prove that I'm not a moron or something and presented not working code. Okay, so let's say feed it 10 and it gives us 3. Let's feed it 1 just to check the edge case, and it gives us 1 like we want. So that is the implementation. Okay, just a note that I'd like to sort of suggest. It's entirely, actually no, never mind. We'll cover that in later in problem C. So how do I say this? If there are no more questions involving problem B, please type the number 12 in the chat so that I can know to move on to problem K. There's quite a bit to cover in problem K, so yeah. Okay, so if there are no further queries, then let's get the problem K. So, okay. So here we have, okay, I'll just pull the problem statement up. Okay, so alright. Okay. So here we have, oh, another problem about sequences. CJ really likes sequences, it seems. Okay. So Kyut Beautiful Abby likes sequences. So looking at past problems. So she makes a sequence A. The terms of the sequence are A sub 1. We've seen this before. So it's probably sort of safe to read it a little quicker. At this point, we're only reading it just to make sure that nothing is particularly different. Alright? So the first term A sub 1 is... So she uses the following rules to make the sequence. First rule. The first term A sub 1 is M. Wait. In problem B, this value M here is 1, actually. So, we've actually already solved a simpler version of this problem before, which is that if M is 1, then it's always just 1 and then it's 3 forever. And if, so now we have to deal with the case where, M is more than 1. So, I'm just curious, was there anyone during the contest who thought while solving B, oh, what if the first term started with any sequence? Tapos nagulat na lang sila na yun nga exactly yung problem C. Is there anyone watching this live stream who had that experience? Okay, I'm just going to assume that no one did, which is perfectly okay. I don't think I would think of that in contest. Anyway, so let's keep going. So again, the second term A sub 2 is the smallest positive integer, such that A1 plus A sub 2 is a composite number. The third term, and so on and so forth. You can read after this scene to make sure that this is the same, but this is the same. Kyut Beautiful Cody's favorite number is n. Now he wonders, what is A sub n? So here, it's sort of the same thing. But it's not because we're now given an additional input M at ito yung bagong start ng sequence. So again, like before, we're going to have to do a lot of thinking, and then the amount of coding, who knows. So how do I say this? So let's see. Let's sort of experiment with looking over these values. Okay. Since again, just as we did a while, just as we did with problem A and just as we did with problem B, we're going to first get our feet wet by looking at simple cases. So for the if the sequence starts with 1, then I know that the next few terms are 3, 3, 3, and so on and so forth. That was what problem B was all about. Now, if the sequence is 2, then if the sequence is 2, then we have that it's a composite number. So it cannot be, the next term cannot be 1 because 2 plus 1 is a prime number. So we have to have 2 because 2 plus 2 is 4, which is a composite number. So we can have wait, for some reason I put stabilized 2. And then again, if we have a bunch of 2's, the next term in the sequence has to be 2, and the next, and so on. Now, what about 3? Well, for problem 3, no, sorry, if the number is 3, then can it be 1? Can the next integer be 1? Yes, because 3 plus 1 is 4, a composite number. So 3 plus 1. Okay. And then, can the next number be 1? Well, no. For reasons we've discussed in problem B, the next number still cannot be 1 or 2. Because then you'd have a sum which makes a prime number, and that's not something you want. So we have to have 3, maybe? 3 plus 3 is 6, 1 plus 3 is 4. They are both composite numbers, so it is okay. So we have 1 plus 3. And similar to n equals 1 with a 1, 3, 3, 3, 3, 3, 3, we can have 3. And so on, so on. It's going to be 3's all the way down. Okay. So at this point, you can go, okay, I have a number 4. And so on and so forth. But, okay, at this point, you might think to yourself, oh, looking for the sequence is so exhausting. I know I don't have anything to do, but do I really have to compute this? If you want to, yes. But there's sort of there's a concept I want to introduce, which might be, it depends. It might be familiar, it might be mind-blowing. I'm not sure how you guys will react to it, but essentially, it's the concept that in programming contests, okay, you can use code not just as the end product of all your thinking and all your implementation and all your debugging, but also as a means to get to that code. What do I mean by this? Looking for the sequence is tiring, right? So why don't we try to automate it? So we're going to try to look for we're going to try to look through how the sequence is computed, look through how we were computing the sequence earlier, and try to put that logic into code. So really, we just turned it into an implementation problem. So I'm going to oh, I realized I forgot to switch. This is the sequence examples from a while ago. Brute force, yes, that is precisely what we're doing. Brute forcing has other uses, which I might bring up later if we get to them. But essentially here, so we're trying to sort of compute and an m, so that we don't have to sort of write the code. Let's just say m is 5 or something, right? So with this m is 5, our logic would be, let's say a is this. Um, a for now is just m, and the idea we have is we want to sort of grow the sequence. So what I'm going to do is this. So I'm just going, since we're just trying to use this code to look for a pattern, let's try to compute, let's say, the next 10 terms. So let's say for next term in range 10. If you're unfamiliar with Python, then range 10 is essentially a list of all the non-negative integers that are less than 10. I mean, technically, it's between 0 and 10, with the 10 being excluded. So range 10 is just 0 to 9. So the effect of this is that whatever is in the for loop will be executed 10 times, which is what we want. Since we want to compute the second term, we want to compute the third term, and so on and so forth until we get to a total of n times. Okay, so let's try to figure out how we'd implement this. So I will use a bit of a Python feature. I will use a bit of a Python feature here. You guys aren't familiar with it. It's the count function from the itertools module. And what the count function does is it essentially allows you to code an infinite loop. So if, let's say, my next line would be for maybe next term in count 1, what this will do is it's going to say, oh, count 1, and then it's slowly going to spit out the next term. So it's slowly going to spit out all the numbers after 1. So it's going to spit out 1, it's going to spit out 2, it's going to spit out 3, and so on and so forth. It's going to be an infinite loop unless I break out of it. And that's exactly what we want. Because earlier we were asking ourselves, is 1 the number? Is 2 the number? Is 3 the number? And so on and so forth. So here we're just getting Python to ask those infinite questions for us. Now, we want to do something like, we want to check. So at this point, we want to check over each previous term and see if the sum is composite. So just as in the implementation problems for earlier weeks, we're just leaving notes for ourselves to keep our work organized. So checking over the previous terms, seeing if our sum is composite. How do we do that? Let's first worry about checking each previous term. So again, we use the Python for loop. So for let's see, previous term in A. Just a note, if you're a C++ user, you can actually replicate this behavior, because I know that there's this sort of, you might do like a for int I and 0, I is less than, let's say, a size or whatever, and then plus plus I. You can also do this. And this does, well, if let's say you had something like int previous term equals a I or whatever, these two are the same in that they both loop over the terms of A this way. For the count loop, I think the best way to do this would be to just implement it as a while loop. So you have this one, and then you go, if while this is not the term I'm looking for, go look for another term. Okay, just a note for users of other languages. Okay, now we want here at this point, we want to check if the sum is composite. So here, let's just magically say that we can. So checking if something is composite is kind of scary. So just as we did in the previous weeks, we'll leave it to future us to worry about. So define is composite. This is how you define a function in Python. So and say value, and then Oh my gosh, no, 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 don't run it. It's an error. Ah, I just made error code on stream. This is so embarrassing. Okay, anyway, is composite. So magic, yeah. I'll just say return true. Okay. Again, we're going to worry about this later. For now, let's just finish this part of the code. So, see if someone's composite. Um, so let's say if. Okay. So this is just like what we had in last week's problem B, where we had a loop, and then we want to see if something in the loop satisfies this condition. So just for simplicity, I'm going to be using the flag technique. So here, usually personally, when I use the flag technique, I usually name my flag something meaningful. Like, let's say, um, uh, wait, what's a good variable name for if this term is really the term? Okay, let's say confirmed next term equals false. Oh no, it's true because right now we don't know if any of the next numbers are composite, right? So for previous term in A, then we have very simple if is composite previous term plus maybe next term, then confirmed next term. Just to check, malinaw ba yung code ko right now or do I need to enlarge the font size? Okay, okay, visible naman. I'll increase it by 1 just in case. So anyway, so confirm next term. We set it to false because now we've confirmed that it's not the next term. So now we just simply have to do an if confirm next term, then what we do is we add it to the sequence. So in Python, list.append just adds an element to list at the back of the list. So here, this would add our next term to the back of A, which is exactly what we want because this is the next sequence. This is the next term in the sequence A. So A.append maybe next term. At this point, it's not a maybe next term. This really is the next term. But that's the variable name we have, so we have to stick with it. And at this point, we break out of the loop because we found our term. So it's possible to write this again, just like with last week and the discussions about flags, about the flag technique. It's possible to write this in a way that uses a function, let's say look for next turn, and then here you'd have the same loop, but instead you do something like return maybe next term to break out of the function and therefore the loop. But a banana is a banana. They taste the same. So you can also do it. So you have different options when implementing code, whichever is more comfortable for you, whichever is clearer and has you do less thinking is generally the better approach you should go with. So here we just have this code. So after breaking, we have to check, is there anything else we have to do? Not really, we just do that 10 times. And then I guess since we're using this to check, we just output the sequence we get. So okay, here. So we do. Remember a while ago we said, oh, we will just let future us worry about how to write the is composite function. Well, too bad for us because we are now that future self. So we're unlucky. We have to write the function. Luckily, we can sort of just interpret the definition literally. So the definition of a composite number is if you have now we're future us. The future is now, old man. Yes. Okay. The good thing about being part of the future is we get to innovate. Sadly, functions to check if a number were composite or is not exactly cutting edge, but it's something, it's something. Okay, so the definition of a composite number is that you have two numbers, A and B, that firstly have a product equal to value, and secondly have A and B both being greater than 1. Okay, so at first glance, it looks like it's going to be hard to use this to compute. But one thing you do, oh no. So one thing you can try to do when you're just flat out stuck on a problem, wait, okay. I just checked if it was my code that was visible. One thing you can do if you're flat out stuck on a problem is to mess with it. So here, you can say, oh, I'm going to mess with it. In school, we were trained to solve algebraic equations, so I'm going to act like I'm solving an algebraic equation. Legit. I remember advice I got from way back when I was still joining IOI that sometimes if you have to do something as stupid as, let's say you're trying to figure out the problem, you drew squares in one place, try drawing it as circles, try drawing it as triangles. If you connected two things, try connecting them with dots instead, or with lines, or draw them differently, or just try to do just try to do things, in short. Okay, so here we're doing things. So we can divide both sides by b to lead to a equals value divided by b. So, now, what observation can we make here involving how a, b, and value relate to each other? Well, here, we know that a is an integer, right? Therefore, we can actually conclude from this statement that value has to be divisible by b. Okay. Is this unclear? Is the reason I was able to deduce this from this unclear to anyone watching? What do you mean? Okay. If there were no comments, I'm going to assume it's clear for everyone. Sige. So now, we've now transformed the definition from something vague, oh, the value is a product of two things that are two things, to something we can actually work with. So here, in this case, the idea now is that we want to try and find some b with a valid a. Okay. So if value is divisible by b, we essentially know that value has to be, no, that b rather has to be a divisor, a factor. So from this, we can try thinking, okay, we can probably try to attack this by looking for all the divisors of b, and then seeing if those divisors of b lead to a value of a that lead to a value of a that matches. I just realized it's divisors of value. So we're looking for divisors of value, and then we want to see if those lead to good pairs of a and b. So looking for all divisors of value, one way to start here is to realize that these divisors have to be between 1 and b, and value, I mean. Is this unclear to anyone watching? The reason why I can't have something like, I can't say something like 20 is a divisor of 10. Okay, if there are none, I'm going to continue. So to address this, we can use a for loop for divisor in range or here, let's just say might be divisor. Usually positive divisors. Okay, that's a good. So you're asking if this value of b here has to be positive. That's a good question. We can refer back to the definition. A positive integer that is the product of two smaller positive integers. So here, a and b have to be positive. So here, the divisors do have to be positive. Yeah. Okay. Um. So here, personally, I use this whenever I'm searching for a something in a set of candidates. The variable name I usually use is p plus that something. The p here stands for potential. To make it clear, I'm going to spell it out. So p potential. So you sort of develop your own idiosyncratic, unique coding style as you continue competitive programming. And I think that's one of the cool things about it. You can just talk to your friends about it, and they'll be shocked that you do things differently. Like, oh, you use a for loop this way? Or some things like, wait, I'm trying to remember a real example. Because my friends just have the weirdest coding styles. Like, one of them codes without using spaces at all, and somehow claims my style is weirder because it's more verbose. Just to give you an idea of the sort of diversity of styles you see. Okay. Anyway, tangent aside. For potential divisors in range 1, value plus 1. Here, where we use value plus 1 because we need value to be in a range. Remember a while ago I brought up that the range loop excludes the second point you give it. So here we add 1 to say no, don't exclude it, include it. Okay? So for the potential divisor, so we use a check to see if the variable is divisible. So if value divisor is 0. If this is unfamiliar to anyone, this is the modulo operator. What it does is it takes the remainder of a thing. So for example, 5 divided by 3 is 1 remainder 2. So the value of 5 modulo 3 is 2. Okay? Just in case. So if this value equals a potential divisor, so from this potential divisor, now we can compute our value of a and b. So here b is our potential divisor, and our a is the potential divisor, but divided like this. We have to use the double slash because in Python, if you divide an integer by an integer, even if the result is a round integer, you're still going to get a decimal. In fancy CS terms, the term is floating point number because of how the numbers are represented as sequences of bits in your computer, but that's already a tangent that you can explore if you want. CS is fun. Okay, so we have this, and now the final condition we have to check is that if a and b are both positive and are less than the number, or in this case, it can be greater than 1. So we just do that check. So if a, we can actually do it this way. If 1a value. So that's one thing about CS is fun. Yes, that's the I wouldn't. Yeah. So this is a cool thing about Python, because if you were to do it in a language like, let's say, C++, you have to write it this way. No, a value. And the reason being that if you wrote it, let's say this way, the computer would probably interpret it as this, right? So it's just like the C equals A or B or K or D from last week, which is that the intention as a natural language thing is there, but the computer completely forgets that we're not talking to it in what the code is, but in what we think the code is. So you end up with something like this will end up being true, which is just like 1 or something. So this is just 1's value, which is obviously not what you want. So there, just another tangent. So if 1 is a value and 1 b value, we check both values. Then at this point we return true because we found the pair of a and b that work. Otherwise we return false. Because once we've exited the loop, we've tried all the values for potential divisors, we definitely know that our value was not here. So we have to say false. I'm just going to delete these comments so that to try to keep the code length short. And that's it. Past us, we've done our job. We've written an isComposite function. Yay. So let's run our function to test. I hope it works. Oh no, is it infinite looping? Oh? Oh my gosh, don't tell me it's infinite looping. Don't tell me I have to debug code on stream. Oh Jesus Christ. Oh Jesus. Oh Lord. Okay. Okay, we'll just good. Okay. Surprise, surprise, you guys get to watch me debug. So oftentimes your code doesn't work. That's a reality of life. That's just something you have to do and something you have to work with. So here, for some reason, you can just like optically see that this is supposed to complete very quickly because judging by our examples, maybe next term is small. Next term we just do this 10 times. So probably what's going on is that for some reason we're computing a lot of maybe next terms. So let's see if the sum is composite. So one way to check one way to check this, let's see, let's check if our composite checker is correct. One method of debugging is this. Basically you just put random print statements around your code to like just to check like how the logic is going. It's a very primitive method, but especially in a competitive programming context, it's just the straight up the most effective. And it just works the most. Oh, this is bad. I see. Okay. So what's happening is that the loop is not stopping. Because remember, we want to stop the loop when we hit a composite number. And it is just not stopping. Oh, that's my mistake. I see. So the mistake here I made was that here we want all. Okay. So just to. Okay, so the isComposite function is correct. Can anyone else identify the mistake I made here? If not, it's fine. Debugging is hard and sometimes you get stuck over the most trivial things. Okay, the mistake I made here is that we're supposed to be checking if all the terms are composite. We don't do that here. Here, we set it to false and true got swapped. Correct. So confirm next term here is whether or not we know that it's next term. So here, the intent is that it's set it to true, and then once we find one term that's prime, we set it to false. But this is not the case, because the check we use to set the flag is if the number is composite. So let's try to fix this. One way to do this would be to so first let's rename the so I think it will be fixed if I just do this, because now if it's not composite, then I know that something is wrong. So if we try to run it again now, I think it will work. It worked, and it printed out this sequence 51333333. Sir, okay. You can reverse the true or false in the function. Um, 1 second. My scroll is not scrolling. Okay. Do you mean something like this? False, true. This is what you mean. Actually, I think this will also work. You just have to remember that if the flag isn't set, your code will end up being false. Like this value is false. So in reality, in this check, you want it to be if not confirm next term. Meaning if the flag was not set by this, then you do the append and break and all not. If you do this, you'd have to rename confirm next term to something like this is not the next term, or maybe something like confirmed not next term or something, just to more accurately reflect what your flag does now. So glad you spotted that different way of doing things. So personal preference, if it works, it works. So oh gosh, now that the bug has been fixed, let's move on. Okay, so we now have this magical sequence finder that works. So what I'm going to do now is I'm going to encapsulate this functionality. That's a fancy term. That's just a fancy term for taking something that's scattered out there. Here in this case, it's just scattered code, and packing it into something we can use in the future, like a function or in object-oriented programming languages. If you don't know what OP is, don't worry. You'll naturally be exposed to it as you learn more programming. Something like classes, or maybe in JavaScript, some things like modules or packages. But here, we're just going to simply turn this into a function def get sequence, and it's going to take an n and m as input, and then we just have to. Okay, I hope Colab supports the mass indent operation. Oh, it does. Nice. So we just put it in a function that computes n and m. So there we go. And then instead of just computing 10 terms, since we have to compute n terms, we have to say n minus 1, because we already have one term of the sequence here, and that's m. So what I'm going to do to demonstrate this is now I have an automatic sequence generator. So earlier we were doing 1 plus 2 plus it's tiring. I think it's personally it might be error prone because you might make mistakes in manually doing it. So we now have the program to do it for us. So for start term in range, so here let's just try, let's say, looking at the terms from 1 to 14, 1 to 15. Here it's 16 because 15 plus 1. So we just have to make it print get sequence. N is first, so we want the first 10 terms, and then start term. So you run this, and it prints none. Okay, this is another quirk of Python. So functions in Py, compared to language where C++, where the language is typed, meaning the compiler has to know before you run a single line of code that this function will return, let's say, an integer or a list or a pair of an integer and a map and a dictionary from string to integer. You get the idea. Python is different in that you can just return any function, any value you want, and there is no compiler. Well, I'm not going to get into the technicalities of things like how Python is run, because personally I don't really know them that well too. But basically, Python just goes, okay, cool, 3, cool, 5, cool, a string, and it just puts the burden on you to know that you know what you're doing. So, tangent aside, the fix here is just the reason we see none is because we have no return statement here in this function. And so Python just goes, okay, you return nothing. So I will say this is none. So the fix is just to return A. To add that return statement that we forgot to add in. And once we run our code, there, we have our pattern. I'm going to get some water. You can already start staring at this to try and look for patterns. Okay. So, what things can we observe? We can observe that, so let's see. We can observe from this that there are a few sort of categories that the sequence falls into. So, we have that some sequences sort of converge. The mathematically speaking, when something converges, it falls into some sort of pattern. So you see people use the term converge when they talk about things like infinite sequences, wherein you have this weird thing that goes first. If you've studied limits, then this is the same term you use. In that, let's say the graph of 1 over x converges, well, no, the value of 1 over x converges to 0 as n goes to infinity, because that's what it does. It goes down to 0. So some sequences converge to all 3s, some sequences converge to all 2s, and some sequences converge to some weird value like 7 or so. Like something like 1 and then 7. So we're going to use so this is what I said earlier, when we're going to add lots of layers, false starts, motivation store, investigation. Now we're going to use these patterns as a springboard for our analysis. So a natural question to ask at this point is, what kinds of numbers fall into what kinds of groups? Because if I knew that, oh, this input falls into the group where it's all 3, 3, 3, 3, 3, then everything is 3, 3, 3, 3, 3, and I win. I can solve the problem. So here, let's start with the 2, 2, 2, 2, 2 group. Actually, no. Wait. Okay, let's start here with the 1, 3, 3, 3, 3 group. So, do you guys observe a pattern in the sequences that go 1, 3, 3, 3, 3, 3, 3? So my question is 1, 3, 3, 3 x pattern for x. When can we sort of expect the sequence to become 1, 3, 3? I'm not asking for a proof right now. That's what we'll figure out later down the line. I'm just asking, just by staring at this list of numbers, which ones end up being 1, 3, 3, 3, 3? Odd numbers. Okay. That's not entirely. Okay, that's like 95% correct, because here you have an odd number 1, which does not go 1, 3, 3, 3, 3. It goes straight ahead to 3, 3, 3, 3, 3. But odd numbers, if you look at all the other odd numbers we have printed out here, which is 3, 5, 7, 9, and so on and so forth, then it does look true that all odd numbers go 1, 3, 3, 3, 3. One thing we can do to further test this is to print more terms. So here I'm going to print from 1 to 50. But now I'm going to do this. So this function, this parameter in Python is known as the step. So here, so when step is given, it specifies the increment or decrement. So I'm going to make it produce the start terms 1, 3, 5, 7, 9, and so on and so forth. Essentially all odd numbers. If we see that all the numbers are 1, 3, 3, 3, 3, we know something is going on and we have to investigate it. So run. And all the numbers are 1, 3, 3, 3, 3. What the heck? Why? Let's think about it. So let's go to the this. Okay. So odd numbers like 3, 5, 7, 9, etc. Because if it's 1, we know what it is. That was problem B. So now we look at odd numbers. So one way, if I computed the sequence for just one of these odd numbers, I mean the computer can do that. I don't really have to do it myself. So what we're after here is a sweeping proof. I'm trying to show for all these odd numbers at once that this sequence will end up being 1, 3, 3, 3, 3, 3, 3, and so on and so forth. So here, one way to write these odd numbers is as, one common way at least, is as 2x plus 1, where x is at least 1. This works because it's like saying odd numbers are those numbers that are not divisible by 2, right? So it's like you take all the numbers that are divisible by 2 and you just add 1 to them. And that's it. You get all the numbers that are not divisible by 2. If you wanted like something like 2x plus 1 equals 9, then you can express it. Let's say you wanted 2x plus 1 equals 9. Because 9 is an odd number, there should be a value of x. And there indeed is. Because x equals 4. Works. Okay. Does anyone not understand why I'm representing it this way? And why this representation works? Okay, if no one, I'm going to continue. So now we have this, right? And we want to compute the sequence. So we're going to do the same thing we did earlier, which is to look at the terms of the sequence one by one, except this time we have this little scary X thing instead of a number. Again, like earlier, don't panic. Okay, let's just proceed like we did with earlier. So we want to find the smallest number here such that 2x plus 1 plus 1, the plus number, is a composite number. So our suspicions say that 1 works. Let's verify that it works. Okay. We have 2x plus 1 plus 1. This is our candidate term, equal to 2x plus 2. We're just simplifying. At this point, we factor out the 2 because remember, we want to show that it's a composite number. So one natural way to show that something is a composite number is by showing that it has factors. And so by doing this, there. Okay. Is everyone here convinced? Like 100% convinced? Like I believe convinced that this is always composite? Do you believe? Okay, so I take it that everyone believes. So what we're going to do is, so we know now that this value is 1. Okay, so we know that this value is 1, right? So wait, it's acting up. Okay, we know this value is 1. So we now want to verify that the next value is 3 and it will keep being 3. So just as with problem B, we know that it cannot be 1 or 2 because that would lead to 1 plus 1 is 2 or 1 plus 2 is 3. Both of them are prime numbers, not composite numbers, which we don't want. So now that fuels our suspicion further that the next term will be 3 and it will always be 3, and we can test that. So here we have let's say 2x plus So here we have two numbers to test, 2x plus 1 plus 3 and 1 plus 3. And we can verify that both of these numbers are composite. Just as with earlier, we write 2x plus 4, and then again, we want to find factors, so we factor something out. So this equals to 2x plus 2, and then 1 plus 3 equals 2 times 2, 4. So indeed, both of these numbers are composite. 2 times x plus 2 is composite for similar reasons that 2 times x plus 1 is composite. Because both of these numbers are greater than 1 and less than our value at, and less than itself, and less than the product at the same time. So we have that this is 3 and that this is 3 for the same reason, because now we just have to check 3 plus 3, 6, and we're okay with that. So, and this will be just be 3 forever. So our suspicion is true that if we have okay, let's just summarize the pattern we find here. So if we have 1, then the sequence will end up being 1, 3, 3, and so on and so forth. And if it's an odd number greater than 1, that leaves us 1, the sequence will proceed 1, 3, 3, so on and so forth. Okay. Do people know how to factor polynomials already? This isn't really treating it in the context of being a polynomial. Here, x is any number, generally speaking. So basically, to give a concrete example, let's say x is 5. So you'd have something like 2 times 5 plus 1 plus 3. And this would end up being 2 times 5 plus 4. And so, since both of these are divisible by 2, I can factor it out and go 2, 5 plus 2. So that's just the basics. If you want to learn more about this kind of algebra, of course, just ask in the server. So that's our investigation. So next, the natural sort of next thing we want to do is the next thing we want to do is to ask, okay, what about the even numbers? Okay, what about the even numbers? So let's go back again to our little simulation thing, and let's try to investigate the case. 1 second. Okay. So, wait. Okay. So, let's try to continue our investigation into whatever the hell this is doing. So since we've solved all odd numbers, now let's focus our attention on even numbers. So here, I ran the same simulation, except this time it's over 2, 4, 6, 8, and so on and so forth, because that is the sequence of numbers that range 252 does. Okay, so now we see a very strange... Now, okay, the pattern here is a bit more difficult to find, right? So here we have some numbers that just always go 2, like for instance 2, 4, and 6, while we have some numbers that do not go 2. So this one 8 goes 17777. This one 14, it goes 17777. and this is 24. It goes 1 3 3 3 3 3 3. And so what the heck is going on? It's not unlike before where it was natural to see that, oh, at a glance you can see all odd numbers go one almost all odd numbers go 1 3 3 3 3 3 3, and we proved it. Here we have to do a little bit more digging to find the case. So let's take note of the first 7 even numbers. 2, 4, 6, 8, 10, 12, 14, and note which ones of them fall into which group. So now, if we just go back into our sketchobile, okay, so we have 2, 4, 6, 8. That's supposed to be a 6. I don't know why. Ugh. 8, 10, and 12, right? So we have that 8 and 14. Okay. So 8 and 14. What's that? Okay. So here we have 2 groups. So we have the 2. Wait, I don't know why. Okay. So we have the 2. Why is it not writing on 2? So we have the 2 2 2 2 2 2 group. And on the other hand, we have the 1 something group. So the non-weird group and the weird group. So the items that go in the weird group, according to our simulation, are 8 and 14. So 8 and 14. And the items that go in the non-weird group are 2, 4, 6, 10, and 12. So what the heck is going on? To further see this, we can try computing some of the sequence. So we know that for these terms, for this group, it's okay for 1 to be the next term in the sequence. And why is this? Well, we can check. For 1 to be the next term in the sequence, it has to be true, to be the second term in the sequence rather, it has to be true that m plus 1 is a composite number. So here we have that m plus 1 composite. And indeed, we can check that 8 plus 1 is 9, which is composite because you can write it as 3 times 3. And 14 plus 1 is 15, which is composite because you can write it as 3 times 5. Okay? On the other hand, here, for some reason, the sequence is not returning 1 as the second term. Why is that? Okay, chat, tell me. In this group, the group where the numbers go 2, 2, 2, 2, 2, 2, 2, is m plus 1 prime or composite? Compositant. Okay. That means the primes and 1. Well, luckily in this case we don't have to worry about 1 really because it's even whatever. Okay. So here we have that. Wait. I am so sorry. When I was doing a dry run of this stream, I really thought that I can just use this whiteboard, okay, but it's acting up for some reason. So we have m plus 1 not composite, and we can verify this. 2 plus 1 is 3, which is prime. 4 plus 1 is 5. 6 plus 1 is 7. 10 plus 1 is 11. And 12 plus 1 is 13. And 3, 5, 7, 11, and 13 are all prime numbers. So we've found a break in the pattern, a division. And so let's investigate further. So let's first investigate this 2 to 2 case, because if you look again at our what our simulation says, then we see here that the one something something case is weird because on top of that we have to tell which number goes next, right? So we have to tell which number goes next. So let's try to get our feet wet first with the 2 to 2 case. So if m plus 1 is not composite, then our sequence is forced to go something along the lines of, okay, this is an even number. So if we wrote odd numbers before as 2x plus 1, here we will write it as, here we write them as 2x. Okay, so here we write them as 2x. And now, 2x plus 1 is a prime number. And so we want to ask ourselves, well, what about 2x plus 2? Well, in this case, just like with the previous, just as in the proof of the odd 1 3 3 3 pattern, here we can factor this out like we did before. Math is hard to do when you're starting out because you have to remember everything at once, but it gets easier, trust me. Okay. So 2x plus 1. Okay. Okay. So with that, just as in the odd 1 3 3 3 pattern, now we've shown that this is also a composite number, and so it's okay. So we know that the sequence goes 2x 2, and then again we still cannot have 1 as a term here because 2x plus 1 is a prime number, but we can have 2 because 2x plus 2 is a composite number, and 2 plus 2, which is 4, is a composite number. So we have 2 and 2 and 2 and so on and so forth. So we can in fact just as a bookkeeping, just so we're organized and we have something to refer to later on when we implement. Wait, let me just okay, let's list it down. So if even and m plus 1 not composite, then we have I'm really sorry. I hope you guys can understand what this says. This says if even and n plus 1 not composite, then the sequence will go 2 2 2 2 and so on and so forth. Okay, so here, so now we have one last case to look at. After all that math, this is it, the final boss. Well, not really the final boss. I actually don't know how hard or easy this is compared to the rest. If m is even and m plus 1 is composite, so just like before, we'll try to sort of make compute the sequence still. So let's see, 2x, we know that the sequence goes 2x, and then since 2x plus 1 is composite, then we're okay with the setting 2x plus 1. Okay, so now what's the next term? Wait, no, I'm sorry, that was wrong. The next term is not 2x plus 1, the next term is 1, because you have 1 as a, because you have 2x plus 1 as composite. Okay, I'm sorry. Anyway, what can the next term be? We know that the next term cannot be 1 or 2 because you have a 1 in the sequence. Can it be a 3? Now, at this point, okay, sometimes when problem solving, you have to sort of stay open. That's sort of the tricky balance, I feel. You have to be open enough to enough possibilities so that you can discover eventually what's going on. But on the other hand, you have to limit yourself appropriately so that you don't get overwhelmed. So here we did the limit ourselves step in confining our investigation only the case where we have m is even and m plus 1 is composite, right? So here we have to be a bit more open now. So we can't right now determine if 2x plus 3 will be composite because we're testing 3. We know that 1 plus 3 is composite, but we don't know if 2x plus 3 will be. So, okay, we just go, sure, maybe it's 3. Okay. Next, we cannot be 4 because 1 plus 4 is 5 is a prime number. Can it be 5? 1 plus 5 is 6, that's composite. 2x plus 5 might be composite. Let's see. Wait, let me just... 5. Might be 5. Can it be 6? No, because that would be 1 plus 6, which is 7, which is composite. So we have to have... we cannot have 6. Can it be 7? 1 plus 7 is 8, that's composite. 2x plus 7... maybe. It might work. So if we're here, then we know that 2x plus 3, 2x plus 5, and 2x plus 7 are all prime. So in this case, a natural question to ask is, can it be 8? 1 plus 7 is... 1 plus 8 is 9, that's composite, so it's fine. But the question I've been ignoring actually, when I've been asking, can it be 3, can it be 5, can it be 7 is, have none of the previous numbers worked? So in this case, let's stop for a moment and ask, is it possible... Okay, is it possible... Wait, for 3... Wait, what? Oh, that's a bad looking 3. For 3, 5, and 7 not to work, but for 8 to work. Okay. So, for this to happen, then all of these 3 numbers have to be primes. So, you'd have to have something like 3, 5, and 7, which are prime. So, let's think about this. Let's think of examples of primes where, which are 2 and then 2. So we have 3, 5, and 7 themselves. If you then have 8, that doesn't work. 8 is obviously not prime. Let's think about... I can't think of examples off the top of my head. Wait. Okay, so... Triple prime... Okay, just a minor fun fact. Never mind. Yeah. We can't... It's very hard to control, like, for sure, which of 3, 5, and 7 first will be composite. But if we know they're all prime, then one thing we can look at is where does this happen? And can it be possible? So in other words, is it possible to have a sequence that looks like prime, composite, prime, composite, prime, prime. So this is the 3, this is the 5, this is the 7, this is the 8. So if you have this scenario, wait, no. Prime, prime, prime. Okay. Let's see we're in a scenario where all of these 4 don't work. Like, let's say we're not done yet. So for that to happen, we have to have 2 primes that are beside each other. We have to have 2 primes with a difference of 1. Can anyone in the chat give me 2 primes with a difference of 1? If no one gave me 2 primes with a difference of 1, you guys are actually correct because there are no primes. 2 and 3. Okay, that's one example. 2 and 3. But here, remember, we're in the context of some number plus 3, some number plus 5, some number plus 7, and some number plus 8. So the thing I want to ask here is, aside from 2 and 3, is there some number such that the number plus 7 and the number plus 8 is prime? Okay, that's the only example. That's correct. Actually, I was just going over it a little slower so that if you weren't aware yet, you can sort of come to realize it. So here, the reason why that's the only example, the 2 and 3 are the only example of primes that are adjacent to each other, is because of this. Okay, um, the only, here's a fact, the only even prime is 2, right? Because by definition, any other even number is divisible by 2, and it being divisible by 2 would make it not a prime, right? Now observe that among 2x plus 7, if they are adjacent, one must be even, one must be odd. Precisely. Tama. So you have 2x plus 7 and 2x plus 8. One of them must be even and one of them must be odd. So one of them has to be 2. But we cannot pull an x from a magical hat that will make this 2. Right? Yes, 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 your thinking is correct. So, in fact, it cannot happen that after 3 fails, 5 fails, 7 fails, 8 will fail. No, that is impossible. We have mathematically proved it. So, here, 3, 5, 7, and then 8. So these are our choices for the third term. Now, what can the fourth term be? So again, since unlike before where we can go, haha, the sequence will always stay the same. Here we're not so sure of it, but it has happened enough that we might suspect that it's true, that the sequence is just forever the same. Let's check. So let's say for example that the third term ended up being 7. The third term ended up being 7. So what will happen now is if the third term is 7, then we know that 1 to 6 cannot be the fourth term because you still have to have 2x plus the fourth term being composite. So you cannot have 2x plus 1, 2, 3, 4, 5, 6. 2x plus 7 is composite. 1 plus 7 is 8, which is composite. And 7 plus 7 is 14, which is composite. So if the third term was 7, then you can keep going actually. 7 and so on and so forth. And so we have that it's true for 7, and you can actually show that it's true for all the other numbers. If you want to work out the logic, just work it out after the stream, but it's basically the same thing in that it's fine with 2x, it's fine with 1, it's fine with itself, and any other number less than it is not fine. Okay? So let's just note down our findings. So finally, after that grueling investigation, we have covered all our cases and we are now ready to code. Let me just get the pen. So let's just write else 1 and then 1 of 3 or 5 or 7 or 8. Imagine nyo na lang na Sudoku to and like this is the possible values. And then after that, the sequence is always constant. So there! That is the pattern for problem C. Now you can go ahead and implement this if you want. And actually, we're going to do just that. But there's just a little something that we want to sort of So actually we can go ahead and compute this right now, because basically now we wanted to implement this in the simplest possible way. This because there are a lot of cases. If we just do the cases, then we might run into errors. We might have to debug each individual case, and we don't really want that. So one approach we can do here is deduce. From this, we can actually deduce two things. First of all, beyond 3 terms, 4 terms, the sequence never changes. It's always either 3, 3, 3, 3, 3, 2, 2, 2, 2, 2, 5, 5, 5, 7, 7, 7, 8, 8, 8, but it will not change. And second, that this starting value here is small. Small enough, in fact, that if we run this loop here, maybe next term, in reality, we can replace this count 1 with something like range 110 and it would still work. Okay, so that's one thing we do. So now we're just going to check over each previous term, see if some is composite. Okay, so now one thing we can do now, okay, we're actually going to try to write code to solve the problem now. So like I said before, to investigate this, we used code not just as an end, as the end product, but as a means to poke further, to do the grunt work for ourselves so that we can focus our time on looking for patterns and proving that what patterns we find are true. I'll say a little something about proving actually, if at the end of the whole discussion, if I have time. So, okay, the fourth term, so input, oh, right, I have to switch, okay. So input consists of a single line containing two integers m and n in that order separated by a space. So we have to do just that. So I'm going to do a little trick here, which is so let's say line equals input dot split, m equals line 0, n equals line 1. Okay, so now what we want to do is we want to compute the first few terms of the sequence. So first few terms equals let's say line we use our function getSequence. So it turned out in the end that the getSequence function really did end up becoming useful because we used it now to implement stuff. So getSequence of this time, now we just want the first first 5 terms. Probably you can get away with 3, but 5 still works. GetSequence 5, and then let's say m. No, yeah, m. Okay. So now we want to do some. We can do something like if n is less than or equal to 5, meaning if we've computed, because this returns m terms, right? If we've already computed what n is, then we just print it. We have to print n minus 1 because the first term in first few terms has index 0, the second has index 1, and so on and so forth. So now we have something like else, then we know that the sequence does not change starting from the third term. So we just have to print first few terms. I think this we want to print the third term, so we have to give it the index 2. So we can actually test this. Let's test this on the sample input. Let's test this on test case 2, this one. So if I give it 2, 2. Oh, an error. Okay. So just like I fell for the very bug in the tutorial, I forgot to convert this to an integer. That is so sad. Okay. That's how programming works. You squish bugs. Okay. Run it again. 2. It works. One thing you have to do though, before you say, oh, the program works, is you have to test it on the weird inputs. In this case, a possible weird input to have is the maximum test case. So here, let's try giving it like 10 raised to the 9, 10 raised to the 9. Run it. So and it said 3, but it took much longer actually for the thing to work. And okay, I'm going to bring something up. If you've seen, like, let's say is composite checking code on the internet, then you might realize that this value check does not go all the way to value, because if this value check okay, I see. Ah, okay, I see, I see. So here, in our code earlier, I think it ended up working anyway because it quickly found a potential divisor. But let's say value is a very big prime and there are no potential divisors. So this code will end up checking through all of them. So for instance, uh, so there are possibility inputs in which this will end up checking through all the possible divisors and we end up losing. So there's a little optimization trick you can do, which is in reality, okay, let's say our potential divisor is 24. Let's say our value is 24. So the possible potential divisors are, I think, 1, 2, 3, 4, 6, 8. 1, 2, 3, 4, 6, 8, 12, 24. And if you'll notice, a thing I've done here is to sort them in order so that you can see there are small divisors and there are large divisors. And an optimization you can make here actually is that the small divisors, so the small divisors are only at most the square root of the value. Is anyone in chat not convinced that this is the case? Okay. I will assume that everyone is convinced. This is because, let's say, so you have a small divisor times a big divisor, right? So let's say that the small divisor was bigger than the square root. So you have that the small divisor is bigger than the square root of the value. And since the big divisor, of course, is bigger than the small divisor, you also have that the big divisor is greater than the square root of the value. Then you have that small times big is greater than the value. Which sounds right. Until you realize that small plus big is the value itself. So, we have somehow managed a way to conclude that it's like saying 10 is greater than 10. If you evaluate that in a Python terminal right now, it will tell you false. It will tell you, no, that's what are you doing? That's not true. And that is really not true. And so what that means is, the assumption we started with at the beginning, which is that small can be greater than square root value, is false. So we have to use this. There are more advanced ways of checking if a number is prime, but usually for competitive programming purposes, this suffices. There's just an NOI LMS problem last year that where you have to use a faster way. I don't know what the problem setter was thinking, but yeah. So we just have to change this from value to something like square root value. So what I'm going to do is I'm going to code something like value times 0.5 value raised to 0.5, let's say plus 5 or so, converted to an integer. Okay? And what this does is it takes the square root tapos nagbibigay siya ng konting palugit in case magkakaroon ako ng edge case somewhere around here, because this isn't an integer and so you can run into issues there. So you have that potential divisor in int range 1 value 5. Yun. So you have that this now just loops over all the values from 1 to the square root of the value. And the rest of the code works that way. And so we've actually written a bunch of code that can solve the problem. Like, this is it. This is it. So there. It was a long and hard journey. We had to write some code. Then we had to look for patterns in the output of that code. Then we had to establish the patterns were true. Then we had to go back and write more code to solve the problem. I just want to say something about the way we proved things. Here's the secret. In competitive programming, you only need to prove things to convince yourself it's true. You don't need to write the convincing proof for the judge, because your code is the proof for the judge. Okay, so if you're confident, if you, let's say you find the pattern like earlier, we saw that if it were odd plus 1, then the sequence is always 1 3 3 3 3. You can just go, okay, this pattern will probably hold. I don't need to prove it. I feel in my heart it is true. It probably works. And you can write your code assuming that, and you can just hope that you didn't make a false assumption. That's a secret. Not really, since I just told it. That you might find weird if you have, let's say, experience in like math or whatever, where usually there's more rigor. But yeah, I just wanted to note that. So okay, if there are no more questions, I will now move on to the latest problem, which is problem D. Are there no questions? Okay, so problem D, the last problem. So we have yet another, wait, my computer is kind of slow. Okay, so we have yet another sequence, right? So we know that, so okay, let's breathe. Wait, I remembered to change this. Okay, so delightful, cute, beautiful, Abby-like sequences. She makes a sequence A. The terms of the sequence are written as A sub 1 to A sub n. She uses zeros to make a sequence. So here we're given a different weird rule. So the first term A sub 1 is m. The second term A sub 2 is the largest positive integer such that A sub 2 squared is less than A sub 1. Okay, okay, that's a weird definition, and the first thing we do in a weird definition is we try to make sense of it. So let's say, for example, A sub 1 is something like, I don't know, 69, right? So the definition says that A sub 2 is the largest positive integer such that A sub 2 squared is less than A sub 1, which in our case is 69. So A sub 2 is less than, has to be some value such that if we square it, it's less than 69. So, okay, chat, give me examples of values which when squared are less than 69. They have to be integers. Okay, 6. Okay, 6 works because when we square it, we get 6 squared, which is less than 64. Which is 6 squared, which is 64, which is less than 69. So that works. So can be 6. Can it be a greater value? Can it be... Actually, no, 6 squared is 36. Oh my goodness. Oh, yeah. 6 squared is 36. So can it be 7? Yes, it can. Because 7 squared is 49, which is still less than 69. So can it be 8? 8 squared is 64, which is still less than 69. Can it be 9? 9 squared is 81, which is not less than 69. So it cannot. And according to the definition, we have to pick the largest possible integer. So it has to be 8. Let's keep going. So the third integer, a sub 3, is the largest positive integer such that a sub 3 squared is less than a squared. So a sub 3, what can it be equal to? Can be 1 because 1 squared is less than 8. Can be 2 because 2 squared, which is 4, is less than 8. It cannot be 3 because 3 squared is 9, which is greater than 8. So it has to be 2 because we want to take largest. So a sub 4 now. A sub 4 can be 1 because 1 squared is less than 2. But 2 squared is not less than 2. So it's 1. And then next, in general, a sub I is the largest positive integer such that a sub I squared is less than a sub I minus 1. If there is no such a sub I, Abby stops. So if, let's say, a sub 4 is 1, then is there some largest positive integer such that a sub y squared is less than 1? The smallest positive integer, which is 1, already gives you 1 squared, which is not less than or equal to 1. So your sequence just stops here. Okay. So one sort of guess we can poke at here is, okay, you'd expect that for a number as high as 69, then we would get a lot of more terms, but they just stopped after 4 numbers. What the heck? Let's try again. Let's poke at that suspicion. This time, let's go for bigger numbers. So this time, let's compute the sequence for a sub 1 is equal to something like 2 raised to 32. I know it's not in the bounds, but we're trying to look for patterns, so it's okay. Our code doesn't have to handle this. So, actually no, this doesn't work. Okay, let's just, yeah, okay, G. So, what is the value? So, because we have that a sub 2 squared has to be less than a sub 1, we have actually that a sub 2 has to be less than the square root of a sub 1. Okay? And since the square root of a sub 1 is around a sub 2, then we have that this a sub 2, since the square root of 2 raised to 30 is 2 raised to 16, so this a sub 2 is something like 2 raised to 16 minus 1. Okay? Here what I just did is I just based it off of this. Okay. So now let's compute a sub 3. So a sub 3 here is, we want to find the values. A sub 3 is less than square root of a sub 2. And here, square root of a sub 2 is around 2 raised to 8. It's slightly less than that, but it's the same. It's around the same ballpark. So we're going to try to approximate by assuming, again, we're just looking for pattern because our suspicion is that it goes down quickly. So because it shouldn't matter if it's like 10 billion or 10 million plus 1, because it will also still go down quickly in the end. So a3 plus square root a2 is approximately 2 raised to 8. Like square root a2 is approximately 2 raised to 8, so this is approximately 2 raised to 8. So far does everyone understand what I'm saying? Am I not producing mishmash? Okay. Alright. So a sub 4 here goes, so same thing. A sub 4 is less than square root of a sub 3, which is approx 2 raised to 4. And what the hell is going on? Because if you look at it, we started with 2 raised to 32, which is so big, you cannot fit it in a C++ integer. At least a C++ signed integer, I think. The maximum value for those is 2 raised to 31 minus 1. And 4 terms later, we have a value we can count on our hands. I'll count. 1, 2, 3, 4, 5... Wait, no. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. If you count in binary, it's just like 1, 2, 4, 8, 16. It's just this. What happened? Why did the number go down so quickly? So that's something we can investigate. Because here's the thing. If we know the number goes down quickly, we can apply the same trick we did earlier, which is just compute the sequence until we know that it hits some pattern, and then just live off the pattern. So in this case, it will go down to 1 quickly, and then it will die. Right? So here, there's actually sort of a way to prove it. So if you follow this approximation, so you have that a2 is the largest integer such that a2 is less than square root a1. Because we want long-term behavior, this is just like thinking about big O complexity. If you want long-term behavior, it's okay to cut some corners here and there. So in this case, we will just approximate this as a2 is equal to square root of a1, because we're just trying to get intuition for how it works, right? So a2 is equal to square root of a1. What does this mean? Well, This basically means you're taking iterated square roots of a number. And if you've ever tried to play with iterated square roots on the calculator, you'll know that it ends up going down very quickly. So, one thing you can do if you're not convinced of this is you can actually look at this example. A sub 1 equals 2 raised to 32 and try to tell what the heck is going on. Well, here, under our approximated sequence, we'd have a sub 2 equals 2 raised to 16. So if you look at it, it's like we just divided the exponent by 2, right? So one thing we can try to analyze is the exponent. So this is another math thing, okay? One thing we can try to analyze is the exponents of the thing. And we get the exponents of this by taking the logarithm of both sides. Okay. Is everyone in chat familiar with the logarithm? Okay, for those who are not aware, essentially the logarithm is like inverse exponentiation, in that if I have let's say for example 2 raised to 16 is 65536, then the logarithm of 65536 with respect to 2 is 16. So it's like it on exponents a number given a base. Okay? And one of the rules of logarithms, one of the identities involving logarithms, is that if I have log of, let's say, something raised to the power of a something, then I can turn that exponent into a factor. So something like this. So here we have that 2 raised to 16. So as an example here, the logarithm of base 2 of, let's say here, we know that it's 2 raised to 16 is just 16 times the logarithm of 2 raised to 1. No, 2. And this is just 1. So it's 16. So once we take the logarithm, since the square root is just taking something to the power of 1/2, then in fact we have log a2 equals log of a1 over 2. So here it's a bit clear, I think, that you have these things, right? You have this logarithm that divides. If you actually try to compute the logarithm for the maximum inputs of this problem, like let's say here, the maximum input is 10 raised to 9. The logarithm is just something like 20 or 30 or whatever. And on top of this being that small, you keep having it, which also makes it even smaller. The reason, if you've never seen this before, then you can imagine, alam niyo yung laro na kung saan may number ka tas sasabihin mo kung higher or lower yung number. Yung tipong 10, and then you go higher, 15, lower, 13, higher, 14. Tama, 14 yung number. Yung game na ganun, alam niyo ba? Okay. So, since, sige, assume ko na lang na alam nyo. So, in that example, eventually, you might end up discovering the strategy of dividing the search space into 2. So, let's say you knew that your minimum number is 1 and your maximum number is 100. Then, you might first ask, okay, 50, is it higher or lower? And the reason this works is because this evenly divides the search space. So, let's say the other guy, they can't give a number such that you end up taking a long time because both possibilities are equal. And what this does is it halves the search space. Binary search, exactly! The reason why this sequence decreases so quickly is the same reason binary search works. It's the same reason if you have things in 2 a lot, you can generally expect it to not take long. This is an idea you can see often in other places. I'm just going to spit out a few Googleable terms if you want to learn more. This idea pops up in Divide and Conquer. This idea pops up in binary search. This idea pops up in segment trees. This idea pops up in a lot of other places. It's one of the core concepts of computer science. The fact that you can divide things, not really core, but it's one of the reasons they work, which is that you can divide things in two, and you can expect the two halves to behave normally. And in this case, the behave normally means they go down quickly. So in this case, it means that our sequence will die quickly. So all we have to do in this problem, so the plan here is just, wait, no, let me write it here. So the plan here is just to write the function to get the next term. That's it. So first we take, okay, so def get next term. So as with before, I will import iter_tools. I will import count so that I can loop over all the positive integers and check, okay, is this greater than 1 or not? Okay, so from iter_tools import count. So for define get next term, let's say n. Okay, so we have so basically for maybe next, so first we have to check, okay, because we basically our plan is to, I know, okay, our plan here is to look for the first, so since we're looking for the last term such that a sub I squared is less than n, we're going to flip that around and we're going to look for the first term such that a sub I squared is at least n. And then we're just going to deduct 1 from that. Is it clear to everyone why this works? Okay, I hope it is clear to everyone, because I will then write so maybe impossible next, I guess. So we code it in count 1. Then very simply, if maybe impossible next squared is greater than n, we break. Okay, so at this point, I will use a funny feature of Python, which is that maybe impossible next is still accessible here. It's still accessible here. It's the value of the last value in the loop it took. So in this case, it's going to be the value of maybe impossible next whenever we ended up breaking. And so in this case, it's the first term we're looking for. Okay? So in other words, we just have to write something like if maybe impossible next. So here, if this is 1, because for a sub I to exist, this has to be at least 1. Therefore, this can only be at least 2. Okay? So if maybe impossible next is equal to 1, then I think we can return none. A while ago, remember how we returned none because it's nonsense and we didn't want that to happen? Here, it makes sense for the function to return none because there is no next term, right? So else, we return as planned the maybe impossible next we find -1. And that's it. If you're concerned about the big O complexity of this function, this works quickly because you will only examine um at most O squared of n values of maybe impossible next, because it's bounded by square root of n. Get it? Does anyone in the chat not understand why this is true? This is the same square root type bound actually as in problem C, the one that allowed us to quickly check if a number even at most 10 raised to 9 is prime or composite, or if it's 1, in which case it's neither. So there, does everyone get why? Okay, if not, I will just continue. So now that we have this is now just a simple matter of taking in the input. So just as in problem C, this is so just as in problem C that I will just copy paste the code. So you can do this, by the way. As you learn more competitive programming, you might find it personally convenient to have a sort of template. That is, you have this pre-written code that you can always refer to and that you just use without checking is this correct without debugging it. As far as I know, most online judges allow this. The only drawback is that contests like NOI finals, IOI, they don't allow template code. So if you want to train for those competitions, you might want to be familiar with them at least. So even if you have it templated, if that template gets taken away from you, you can still write the code well because you still know what the code does, right? Personally, I don't use templates myself because of that reason, but there are contests later on, especially at the college level, where it becomes convenient because there are just these algorithms that you cannot afford to spend time debugging because they're kind of already a bit complex and they're getting of one detail wrong, which you very possibly can happen if you're just implementing off the top of your head, can ruin your life. Not your life, your contest performance, right? So now we've read, and we have to do a sanity check, make sure that the input is the same format. In this case, it is, containing two integers n and m in that format, right? So now at this point, we just basically go, okay, as with before, we will do a generate terms, and then we will pass it an input of m. So this is because later on we want to do something like a equals generate terms m, and then if length of a, so if n is at most the length of a, meaning that we generated the value of a sub n, we just very simply print out a sub n minus 1. But otherwise, then we print negative 1 because no such value exists, right? So now we have print negative 1. So again, same scenario as earlier, where future us we have to write as generate terms function, but in this case it's simple. A is m, and then let's say next term equals, okay, in Python this basically means the last element of a list. If you're coding in C++, then this would look something like a.back. Okay, so next term we just call our get, what did I call it? What did I call the function? Get next term. Okay, so here we just call get next term a sub I, and then we basically, while we still have a next term, so remember earlier we return none from the function if we have no next term. So here we do while we still have a next term, we just add that next term to the list, and then out of our magical hat we pull another next term there. So now this will happen, and of course at the end we just have to return a. So there. Now of course we have to make sure that the code actually works, so let's go run it. The sample input is 7 2, and it outputs 2. Please be 2, please be 2, please. Yes, it is 2. And then we run it again. This time passing a 3 and 3. And we get a value of 1, which is correct. And so that is the solution to problem D. The main idea is realizing that the sequence goes down very quickly. And when you see problems like this, generally that's the first thing. Like when I saw sort of this recurrence, that's the first thing that came to mind. Um, okay, so that's it. One last note before I ask if you guys have any closing comments is that if you look at the standings here, okay, if you look at the standings, you'll observe that um, lots of people, um, D is more solved than C generally. If you look at these scores, that this 100 means solved, 0 means they attempted it, blank means they did not. So more people solve D than C. Generally, in programming contests, especially large-scale ones, the more people solve a problem, the more approachable it is. And so here, you could probably comment, especially given the amount of time we spent explaining. I think C took an entire hour to build up and find the pattern and observe. Well, D was mostly just a one-shot. Observe this and you're done. Well, you're almost done. You still have to write code, but you're almost done type problem. And this was actually brought up in like the group chat of the setters. And I believe CJ's reply was something along the lines of, this will teach the contestants to read all the problems. And in this case, I'm actually pretty happy. And I think if he were the one streaming, I think he'd be pretty happy too. That people did end up reading all the problems, and that in the event that they found C unapproachable or they couldn't figure out the proper approach, and they still had D to try and solve. This will be important, especially as you do harder and harder contests like let's say the NOI or the IOI or other countries' national Olympiads, because not all the problems will be approachable, first of all. Second of all, not always the problems are given in order. In sites like Codeforces and AdCoder, and here in ABaKoDa mostly, you're given the luxury of a problem order that is sorted by difficulty. So your brain can just, okay, do A, solve it, do B, solve it, do C, think for a while, solve it, keep going. But in contests like NOI finals, in contests like IOI, the problem order is generally alphabetical, which doesn't always correspond to difficulty. So the task of being able to figure out which problem is the hardest, which problem is the easiest, which one takes more time, which one needs more thinking power, more implementation power, that is a task that falls to you, usually. So starting now, it's generally a good idea to develop that mindset, because strategy is honestly quite an important part of programming contests. So that's all I wanted to say for this week's contest. So if you have any other sort of things you want to say in the chat, or comments about how you felt the contest, how you felt the explanation was, if you're curious to learn more about things, yeah, please let me know. Okay, so since there are none, I guess I can end the stream now. This notebook, I think I'm not so sure actually. It will be available in some form. I guess I just have to clean it up. Is STEM hard? Okay, random question. Is STEM hard? It depends on the person, I'd say. It depends on how passionate you are about it, because if STEM is hard, that doesn't really mean anything if you're persevering enough to overcome that hardness. If I'm making sense. In the sense that if you like, sure, let's say like, I don't know, like chemistry or physics or something. Personally, I don't have the greatest affinity for those subjects. I mean, I can do well, but not as well that I'd feel confident attacking it, attacking it with more layers and with more depth as people would do, let's say, in college or in the industry. So, um, I eventually decide I don't really imagine myself taking up a job in those fields. And so I think STEM generally works in that way. If you can, if you enjoy it, I'd say, then it being hard won't matter. But if you don't enjoy it, then it being hard, if you don't enjoy it and you're, I guess, a natural born genius, then lucky for you, I guess. But if you don't enjoy it and it doesn't click and you have difficulties, you won't be able to persevere against those difficulties that well, I'd say. Of course, there are other reasons that might factor into your consideration for taking a strand, like practical considerations, career considerations, but just from my perspective, I'd say that's what I have to say. hmm Anyway, back to the this thing. Uh, I'll clean it up a bit, add some more helpful comments that aren't just stream of consciousness remarks, and it'll be available somehow. If you have any more questions, um, I you can just comment in the NOI Discord. If you're not there yet, I believe you should message the Facebook page so that you can get an invite. Um, Other than that, I guess that's all I'd have to say. And see you guys next week, I guess.